This is the screencast for section 6.1, example 6. We're going to construct a slope field. So first of all, a slope field is found by using your derivative because that's what gets your slopes. This slope field is going to direct us to see a visualization of what the antiderivative would look like then. You can see a representation of what all these, a few of the tangents of the original function might look like. Alright, so let's see how this goes. Construct a slope field for differential equation dy dx equals cosine of x. Alright, so the first and maybe easiest set of slopes I can do is when x equals 0. I see that first of all, my derivative only depends on x. And in your homework, you will see, your classwork, you will see that you have derivatives depending on both x and y. So sometimes you need to plug in an x coordinate independent of the y coordinate. But this time, this derivative only depends on x. So I'm going to plug in, let's say, 0. So cosine of 0 is 1, so that means when x is 0 all the time, no matter what y is, because this doesn't depend on y, the slopes are 1. So now I'm going to, where x equals 0, draw all these little mini tangents that have the slope of 1. Same thing, so all the way through the y-axis basically. Alright, well now let's plug in something that is also easy, maybe negative 2 pi and 2 pi, they're going to have the same cosine value. If I plug in negative 2 pi at the derivative, cosine of negative 2 pi is 1, which is the same thing as plugging in positive 2 pi. So now I can draw my little mini tangents that have a slope of 1. Over here at 2 pi, and again here at negative 2 pi, because all of those little tangents where x equals 2 pi or x equals negative 2 pi are going to have a slope of 1, no matter where in this family of curves, this whole field of slopes. Alright, next let's try, I don't know, negative 3 pi over 2. So I plug in negative 3 pi over 2, and the cosine of negative 3 pi over 2 is 0, which is the same thing as the cosine of positive 3 pi over 2. So now I can draw my horizontal mini tangents in my slope field at those two x values. Next, how about negative pi and positive pi? Cosine of negative pi and positive pi are both negative 1, so the slopes would be negative 1 at each of those x values. And finally, at negative pi over 2, the cosine of negative pi over 2, so the derivative evaluated, or the slope evaluated at negative pi over 2 and pi over 2 would both be 0. So again, I have horizontal tangents at each of those x values for those key points, regardless of what y is. So now you can kind of see, what is the antiderivative of cosine? Yeah, it's sine. And look at what these tangents are doing. They're kind of directing your sine curve in the shape it is supposed to be. Now try problem number 29. Says construct a slope field for the differential equation, and in each case copy the graph at the right and blah blah blah. Okay, we're going to do the same thing as example 6, but instead of making up our own slope field that's humongous, usually the problem will give you a window range that they want you to create your little slopes at. Alright, so first, again, the y coordinate doesn't matter, which makes this a lot easier. I don't have to plug in 1 and 1 to find out what the slope is specifically at this point, or 1 and 2 to find out what the slope is specifically at this point. I just need to know what x is to know what the slopes are. So I'm going to start easy. I'm going to plug in 0. The slope at 0 is 0, so I can draw in all my little mini tangents, my horizontal tangents. How about negative 1? So the slope at negative 1 is negative 1, so I'm going to draw those little mini tangents. And then I've got, how about at positive 1? Oh, look at that, the slope is positive 1. So I'm going to draw in those mini tangents. Now, remember, the derivative of this function y is x. So if I find the antiderivative, I get y equals 1/2 x squared plus c. There's your parabolic function that could be vertically shifted up or vertically shifted down, depending on where in the slope field we started. Now, as a little tip for you, sometimes you will be dealing with slopes that are of 1 and of 2 and then of 3. I like to, if it's hard to tell the difference between, like, say we went over here and the slopes at 2 were 2. Well, it's hard to tell the difference between 2 and 1, a slope of 2 and 1, when you're dealing with the little mini tangent. So I would put little mini 2's next to it and little mini 1's next to these, just so that my grader can see clearly what slope I'm working with on both of those types of tangents. Now I quick want to show you an examples with y's in it, because it can get a little bit different. In this case, number 30, the derivative is always equal to the y coordinate. So what that means is if y is -1, then the slope is -1. So anywhere y equals -1 down here along this horizontal line, so -1, -1, 0, -1, 1, -1, those will all have the slope of -1 for the slope field. Now if y equals 0, the slope is 0. If y equals 1, the slope is 1. If y equals 2, the slope is 2. So it's slightly different than if the derivative equals x. Now in 31, we have a combination. The derivative involves both x and y. So now each and every single point is going to have to get calculated. Now, of course, you'll be able to see some patterns, but really this is an independent calculation. So the first point I'm going to try is -1, -1. So I'm starting here down the bottom left corner. X is -1 and y is -1. So if I plug in -1 for x and -1 for y, at that point only is the slope going to be -3. Now the next one I can try, maybe I'll go up one, so -1, 0. If I plug in -1 for x and now 0 for y, this point right here at -1, 0 gets the slope -2. Try another one. Let's go up one more. So -1, 1. So -1 goes in for x again, 1 goes in for y, so my slope there is -1. Now see how I'm labeling all these, because otherwise it'd be hard to tell which one had a slope of -3, which one had a slope of -2, which one had a slope of -1, etc. Now I can calculate all those. That's why they usually give you a pretty small window for doing a slope field, and eventually I get the following slope field, where each and every slope is just a little bit different. I mean, some are repeated, but I had to calculate them separately. And yeah, I could pretty much do that in my head, so showing just a few examples would be plenty.